Hello, this is my presentation on my fuzzy logic paper one. This is Spencer Scott, and the paper I read was Fuzzy Logic in the Arts, Applications in Audiovisual Composition and Sound Synthesis. So in the paper, there's two artistic approaches covered. One is a mapper for audiovisual composition, which we'll get into more detail later. And the other is a particle-based fuzzy logic approach to creating unique and new sound synthesis. So we'll start off with the fuzzy mapper for audiovisual composition. So basically, this system takes either audio or visual images and creates an output that is both audible and visible. So to put this simply, if you give the system an audio input, it will create a visual input that kind of matches that, and then adds the two together into one file. And vice versa, if you were to create a visual, if you gave it visual images, then it would create an audible output and add the two together. So with the fuzzy system, some of the parameters for the inputs are frequency, intensity, duration, and tibre. And then the outputs would be color, shape, size, and motion. So this is with the audio being the input and the visual effects being the output. So here are some membership functions. As you can see, they're all different based on what trait the author was trying to capture. So for example, frequency, you can see has a very large, what is called a very high rating of frequency. So that ranges anywhere from 1,000 to the graphs are kind of hard to read, but I think it's 20,000, which is the human hearing range. And as you can see, like the lower frequencies have smaller functions, membership functions. So, very low, low, medium, high, and very high, you can see are completely different functions in this regard. Things, whoops, things like duration, are evenly distributed between the different membership functions. And then intensity is different because the way people perceive volume can be very different from how loud it actually is. So in the negative dB range, I think this is like 70. It's kind of hard to hear that anyways. It's something that low, so that's why the very low is a bigger range. And then as you can see, as the dBs increase, then it becomes more linear. So that's just some of the membership functions and how they were defined for this particular case. So possible rules. The author has defined some rules that he used for his system, but you could create any sort of rules if you were to create your system of your own, such as if the intensity is high, then the frequency is low, or if the tibre is very low and the duration is medium, then the intensity is high. And you can make them as complex or simple as you choose. And he illustrates that in some of the fuzzy rules he uses. So moving on to the next approach, a particle-based fuzzy logic approach to sound synthesis. So this fuzzy system defines particles within a soundstage based on previous particles to generate unique sounds. So it's kind of just a complicated way of saying it defines a specific variable in space. So it gives it a location in space, each particle, as well as like frequency and other factors. And based on that particle and the particles close to it, it creates um, a new type of sound and a new what is called a sound stage. And you know that way you can tell if it's coming from the left or the right, and you really get a better feel for new and interesting techniques and um, different ways to generate sound. So I kind of went over this a little bit, but the inputs to this are frequency, charge of a particle. So in this case, a charge could be anything from +1 to -1, and this would affect how it interacts with the other particles. Intensity, which is again how loud it is. Position in space, kind of talked about that. Just a XYZ coordinate within an area. And then external influence. These are things like noise. So if a certain particle is particularly noisy or not noisy, and then time that it's there. And so as you can see, the outputs are pretty similar. They're also frequency, charge, intensity, position, and space, but the external factor is not there, as well as the time. Oops. Okay, so here are the membership functions for this particular scenario. So the frequency in this scenario is very much the same for all membership functions. It's proportionate to each of them. Intensity is the same as in the previous example. Space and position is also very much proportional. And then, you know, most things here are evenly distributed. And so what makes the unique sounds is what we're going to get to next, which is the different rules that you can apply to this function. So such things as if the frequency is very low and the charge is low, then the time is high. Or if the time is very high and X, Y, and Z are close to the left, so then the intensity is very high. So I guess to explain X, Y, and Z better, the author defines them as either close to the left, in the center, or close to the right. And so in a sound, in an audio world, this would be such things as like a mono or a stereo signal. So you just have a left and a right channel. Not really a 3D or surround sound type scenario, but it would help with creating different and unique sounds for a stereo type scenario. So in conclusion, these methods demonstrate basically an interesting way to use fuzzy logic. It's a way that isn't really initially thought of, but I thought it was very interesting because it creates a artistic output. And the author also goes on to say that it's not necessary to be precise or for the system to be stable or for the rules to make sense or anything like that. It's because the output is artistic. He's just looking for different ways to create new sounds other than the traditional synthesis techniques, which have become very popular and in that regard have become very much the same. And so this is an interesting way to create new and different techniques that can be helpful when trying to create a new composition or something like that. Hopefully you enjoy my presentation, and if you have any questions, you're welcome to email me. Thank you.